Right. Welcome back to the session for the last talk today. So the last talk is given by Dr. Ryusuke Hamazaki from the Institute of Physical and Chemical Research, and the title of his talk is "Speed Limits in Non-Equilibrium Dynamics from Population Biology to Microscopic Quantum Transitions." So welcome, Yusuke. Yeah, and the floor is yours.
Thank you very much for introduction. And first of all, I'd like to thank the organizers for inviting me to this great interdisciplinary workshop. And I'm Ryusuke Hamazaki from RIKEN, Japan, and today I'd like to talk about speed limits in non-equilibrium dynamics, which are universal constraints that can appear both in classical and quantum systems. And today I'm especially talking about our recent results on new speed limits that are relevant for the population biology as well as macroscopic transitions. So this talk is based on these two papers, one of which is done in collaboration with Kyosuke and Ryusuke, who are the biophysicist and mathematical biologist in RIKEN. And I recently wrote a review paper on inequalities in non-equilibrium quantum systems. So if you're interested in, please look at it. So here's the outline for my talk today. We first give a brief introduction to what are speed limits first, and then I'd like to talk about our results on universal constraint on nonlinear population dynamics. And in the third part, I'd like to talk about speed limits that are useful for macroscopic transitions, and finally, I conclude my talk. So let's begin with the introduction. So looking around nature, we find that there are a variety of state transitions. For example, if we consider a very small scale, like an atom, we can see that the state of an atom can change from a ground state to an excited state, but with obeying this type of Schrödinger equation, which is a fundamental dynamical equation for quantum mechanics. In contrast, if we consider a different system, like a system attached to a bath, then the transition is often described by this type of classical master equation. So this is a thermodynamic transition. Or we can also consider a very different type of non-equilibrium transitions. For example, we can think of the transport of classical or quantum particles to a distant place, which are of course important example for the non-equilibrium transition. And although these three examples are often treated in physics, we can consider a different type of state transitions. For example, if we look at an ecological system, then we can see that the population changes in time. So this is also an example of the state transition in a very different scale. So, and then the natural question is what kind of universal features we can extract from such dynamics. And in this talk, we especially focus on how fast a state can change into another state. And as seen from the following examples, it turns out that the speed should be constrained by some physical quantities. For example, if we consider a quantum system, we can see that the time derivative of a quantum state given by this psi is governed by this h, which actually describes the energy scale of a system. So from this equation, we can see that for a fast transition to occur, energy scale cannot be small. Or if we consider thermodynamic transition, we intuitively know that a fast transition requires the appearance of irreversibility. So this means that for such a system, for a fast transition to occur, entropy production cannot be small. So there are physical examples, but speed limits are important because they can describe such constraints as rigorous inequalities. So let us first consider the example of a quantum system, and actually speed limit are first obtained for a quantum system in 1945 by Mandelstam and Tam. So they consider a Schrödinger equation, which is given like this, and let us consider time-independent observable A, which describes, for example, atom position, momentum spin, or the population of the ground or excited states. Then given such observable A, we can formally write down the quantum expectation value of A like this. So this is kind of a technical point. And then Mandelson and Tam proved this type of inequality. The left-hand side is a time derivative of the expectation value of an observable. So this provides a speed of the expected observable. In contrast, the right-hand side includes delta A, which is a quantum fluctuation of A, and also delta E, which is given like this. So this is the energy fluctuation. This means that this quantum speed limit actually bounds the speed by the energy fluctuation, which is of course an energy scale of this quantum system. Okay. Yeah, as the next example, let us consider some stochastic systems whose distribution is described by this classical master equation. And again, let's consider time-independent observable A, which is given like this, where I is a basis of the state space. Then the expectation value of A is given like this, where Pi is a probability distribution. Now, from the inequality which is obtained in this paper, we can immediately find this type of classical speed limit holds exactly. The left-hand side again describes the speed of the expectation value, and the right-hand side includes the so-called dynamical activity and entropy production rate. So this is a notation for the under the detailed bound condition. So dynamical activity intuitively means that it determines the intrinsic rate for the transition, and the entropy production rate describes the irreversibility content. So this classical speed limit means that in such a classical system, the speed is upper bounded by the irreversibility content through this entropy production rate. Okay. So as for these examples, various types of speed limits are investigated very actively, but the previous results are mainly limited to linear systems like linear Markovian systems or quantum systems, and also their applicability is limited to small systems. So in this talk, we kind of we want to overcome these problems. And yeah, first, as a first topic, we consider speed limits that are relevant for nonlinear population dynamics, such as ecological or evolutionary systems. And in the second part, I'd like to talk about speed limits that are useful for macroscopic transitions, which include kind of transport of particles. So let me talk about nonlinear population dynamics. And in search of such universal speed in population dynamics, we need to consider several things. First, population dynamics is described by a deterministic dynamics of population density, usually, not the probability, unlike the probability distribution in stochastic systems. And also, population dynamics in general includes nonlinearity, which may cause the bifurcation. So what happens in such cases? And also, in certain population dynamics, it is known that the so-called Fisher's fundamental theorem applies, which dictates the relation between the increase of the average growth rate and the variance of the growth rate. So we want to relate our speed limit with the known result. And actually, we have succeeded in doing this, and we derived speed limits for such population dynamics using dynamical equations of proportion types, like genotype or species. And our results can be regarded as one of the generalizations of the Fisher's fundamental theorem. And also, we found interesting critical speed limits with universal exponents around the bifurcation point. So let me tell you the detail. So we consider general population dynamics, which is given by this dynamical equation, where Ni is the population density over type I. For example, if we consider natural selection with mutation, Fy is given like this. Si is the growth rate for type I, and Mij is the mutation rate from type J to type I. Okay, although this Ni is not normalized, we can define a proportion of type P, which is a normalized quantity. So P is defined from dividing Ni over n tot, where n tot is the total number of population density, and substituting this into this equation, we find this type of equation where nonlinearity generally necessarily appears in the second term. Now we consider observables next, and yeah, here in this section we consider time-dependent observable A, which is given like this. Although we have considered time-independent observable previously, so this is this is to generalize our discussion, and we ask how the expectation value A, which is defined like this, evolves in time. Okay. For this purpose, we define the characteristic speed of A as follows. So this VA, to know the meaning of this VA, let us consider its inverse. So this VA inverse gives a time scale for the change of the expectation value of A becomes indistinguishable from the statistical fluctuation delta A. So from some initial time, after the time VA inverse, the change of the expectation value exceeds this fluctuation. Okay? So VA is a corresponding rate for this time scale. And then we have the following speed limit. So V lim is a bound which is described with the classical Fisher information in the information theory, given like this. So this result, this is our first main result, and this is an information theoretical speed limit because classical Fisher information appears. And I note that similar results were known for linear systems like quantum systems or stochastic classical systems in these papers, but it is applicable even for nonlinear dynamics. Okay. Now, before talking,
sorry, may I ask a question?
Sure.
In the previous slide, so the average of A is time dependent because A itself is also time dependent, and also PI is time dependent. Is that correct?
Right. So
both are time dependent.
Both are time dependent. So if AI is time independent, then this value vanishes.
I see. Okay.
So before talking about examples, let us outline the derivation. From the definition, we find this type of equality. And since Pi is normalized, we have this condition. And also inserting Pi and 1 over Pi here, we find this equality. So this is nothing but the covariance between A minus bracket A and del Tp over P. So this is also known as a continuous time price equation. And now, using the Cauchy-Schwarz inequality, we find the covariance is bounded from above by the variance between these standard deviations between these quantities, and we find this inequality. So from this simple derivation, we find that the equality condition is achieved when this A minus bracket A is parallel to del Tp over P. Okay. Now, as a first example, let us consider natural selection with mutation, Mij equals to 0. And in this case, the fundamental equation is like this, which is also given like this. And in this case, without mutation, it's known that the so-called Fisher's fundamental theorem applies. So this states that the increase of the average growth rate equals to the variance of the growth rate. In equation, we have this. Okay. And we argue that this theorem is a special case of an inequality with equality condition. To see this, we first notice that this S minus bracket S is parallel to del T over P from this equation. So this is nothing but the equality condition for this for our general inequality. So we find this. And from the definition, Vs and Vlim are explicitly calculated like this. So this is equivalent to this Fisher's fundamental theorem. But we stress that our inequality itself holds for more general observables, which may not be the growth rate, and also for general dynamics, which may contain the mutation. So now let us consider natural selection with mutation, which is given like this. Here we show some numerical results with taking parameters like this and change this R, which is related to this growth rate. And as observables, we consider we consider growth rate S and entropy, which are defined like this. So there's a graphs, a time evolution of our bound Vlim and Vs and Vi, which correspond to these observables. And from these panels, we find that our speed limits Vs Vi is smaller than Vlim is confirmed for various values of R. Okay. And here we have defined RC, which is actually the bifurcation point for this evolutionary dynamics. So this dynamics exhibits transcritical bifurcation. And around such bifurcation points, we find interesting critical speed limits for the speeds Va, and so this means that so this is represented like this. Va and Vlim exhibit this critical scaling. So let's consider the critical point R equals to RC. Then we have this critical slowing down, whose exponents alpha A and alpha lim Tc are defined like this. And actually, we find that such parallel decay of the speeds as shown here. And for more general RC, from this critical scaling, we find that by appropriately normalizing this Va and Vlim or R minus RC, we find that different results for different values of R collapse to a single curve like this. So this scaling collapse means that this critical scaling holds true actually. Now then, from our general results of speed limits, Va is smaller than Vlim for any A, we can see that around critical points, we find this type of universal inequalities for the critical exponents. So this is our second main result. And importantly, these bounds on critical exponents, alpha lim Tc and beta lim Tc, are universal, which mean that they are determined only by the type of bifurcation, irrespective of the details of the dynamics. So for transcritical bifurcation, we find that alpha lim Tc equals to 3/2 and beta lim Tc equals to 1. So since this is universal, this can be found for different models that exhibit transcritical bifurcation. For example, if we consider SIR model, which is a simple model for disease infection, it is known that the transcritical bifurcation occurs, and even for such a case, which is not the evolutionary dynamics, we also find the same inequalities for the critical exponents with same critical exponents. Okay. In contrast, if we consider different type of bifurcations, like Hopf bifurcations, we have different inequalities. For example, if we consider the competitive local Voltaire model with Hopf bifurcation, we instead have this type of inequalities. So here's the summary so far. Using dynamical equation of proportion types, we derive speed limits based on Fisher information for general nonlinear population dynamics. And this speed limit generalizes Fisher's fundamental theorem and is applicable for evolutionary dynamics with mutation too. And our constraint indicates non-trivial bounds for critical relaxation exponents around bifurcation points, which are universally determined only by bifurcation type. Okay, then let's go on to the next topic, speed limits for macroscopic transitions. Yeah, so in this topic, we consider a different situation, and we consider the following transport problem. We assume that some particles are transported to a distant place, and we assume that the transport distance is much larger than the intrinsic length scale of a system like lattice constant or lattice constant. So in that sense, we call it macroscopic transitions. Now let us consider average position of m particles as an observable. Then using the conventional speed limits obtained previously, we find these types of inequalities. So we showed the case for the quantum system and classical systems. And actually, both of these inequalities fail for such macroscopic transitions. So this means that the bounds become meaningless. To see this, we first notice that the left-hand side, which is the actual speed of the which is the actual speed of the average position, is of course convergent, meaning that this does not grow with L system size or M or time t. In contrast, the right-hand side typically diverges and becomes meaningless. For example, this delta A, which denotes the width of the particle distribution, diverges unboundedly because of the diffusion. This means that conventional speed limits fail for macroscopic transitions. So our motivation is to ask if there is a useful speed limit for such macroscopic transitions, and if it exists, to what extent it is applicable. And we found the affirmative answer. And for a class of physical quantities A, its speed is upper bounded by the product of the gradient of A and the quantity base of the probability current. And this gives the expected order of the speed. And actually, this framework is applicable from classical stochastic systems to microscopic quantum systems. So our general idea is to map the system to a graph structure to treat a general discrete system. Yeah, so this is related to the previous talk. And here the vertices are defined from the basis of the state, and the edges are connected if and only if I is not equal to j, and if there's a transition between I and j. As a simple example, let us consider two particles on 5 sides with neighboring hopping, and we assume that double occupancy is prohibited. Then we find that there are 10 bases like this, and also the edges are connected from the knowledge of the neighboring hopping like this. So this means that this system is mapped to this graph structure. Okay. Now, with such graph, we define probability distribution pi on this graph. And then for typical physical processes, we can assume that the local continuity equation probability holds which are given like this. So JJI is a probability current from vertex I to vertex J, and JJI also satisfies that I and it's anti-symmetric between the exchange of the I and J. Now, before showing our result, let us remind of the derivation of the conventional speed limits. And in this section, we consider time-independent observables. And as I said this previously, this time derivative of the expectation value can be given like this. And using the Cauchy-Schwarz inequality, we find this type of inequality. But as I said, delta A is divergent for macroscopic transitions. So we want to avoid this derivation. For this purpose, we instead use the continuity equation of probability from this part. Then from this, we find this type of equality. And using the anti-symmetricity of J, we find delta over this time derivative can be given like this. Now we can use some inequality. We find this type of inequality. So this is our main result. And here we have used the Helder inequality, although we can also consider a different version using the Cauchy-Schwarz inequality.
Just clarification.
Okay.
So do you consider the reversible edges right now? Or is it directed graph?
It's not directed. We consider undirected graph
Okay.
yeah, for our formulation.
Okay.
Yeah. Okay, so importantly, this bound includes the maximum difference between AI and AJ, where I and J are connected by the edges. So we can regard this quantity as a gradient of A defined by the edges, or it can also be regarded as a discrete version of the Lipschitz constant on the graph. The important point is that for typical macroscopic dynamics, this gradient term is much smaller than, for example, the fluctuation as we see below. So because of this relation, convergent useful bounds are obtained from our method. So let me first consider classical master equation, which are given like this, which is given like this, and this can also be given like this, where JJI is a probability current. Then after some calculation, we have this type of inequality. So we skip the detail. So this includes entropy production rate and dynamical activity. So let us compare with the inequality which we have seen in the interaction, which is given like this. So here the normal of A is defined as the maximum of AI on the vertices. And actually, for many macroscopic observables, we have this inequality. So gradient term is much smaller than the norm itself, which leads to the fact that our inequality is much better than this inequality. Okay. Okay.
So if you compare those two, inequality, the yours and 2018 one, can you say that one is always better, or the current one is always good for the macroscopic observable compared to the previous one? I just want to understand the relation between those two inequalities.
Yeah, I think for some cases this is better for non-macroscopic transitions. So in a small system, I think this can be better than this, and or vice versa. So it depends.
Okay.
But for macroscopic transitions, for like macroscopic transport of particles, then I think this will be better.
I see. Thank you.
So as a simple example, let us consider macroscopic transport of M particles in symmetric simple exclusion process. So this is a model where particles can hop without double occupancy with equal probability Q equals to 1/2. And we consider an observable which is given by the sum of the particle distance from the origin, d. In this case, we find that this gradient term equals to 1, which is much smaller than the norm of d itself, which is divergent with respect to M and L. So our inequality becomes quite well. And yeah, from this is a numerical result, and we find that our speed limit works well. And as a comment, in this case, the detailed balance condition holds, but even without detailed balance condition, we can find a similar but modified inequality turns out to be useful using the so-called Hatano-Sasa entropy production rate, which is one of the non-equilibrium entropy production. Yeah, finally, I'm going to briefly introduce the case for the quantum microscopic systems. So in this case, we consider general quantum dynamics, which is defined, which is given this Schrödinger equation, and psi is the so-called state vector for quantum system. And it is known in quantum systems that the probability is given by the square of this psi i's. And defining such probability distribution, we have this type of local continuity equation. And in this case, the current is very different form from the classical stochastic systems. So because this current, the form of the current is different, then we have a different type of speed limits for an observable whose expectation value can be given like this. So we find this type of inequality, and we again have this gradient term, which is very important for microscopic transitions. In CH, and instead of the entropy production rate, we find a bound that includes CH and E trans, which are defined like this. So they are strengths of the transition, which is easily known from if we know the dynamic, know this Hamiltonian, and E trans is the transition energy, which is also a physical microscopic observable. So let me summarize the second part. So we derive speed limits that are useful for macroscopic transitions based on local conservation or law of probability. And they are described by the gradient of the quantity and the probability current. Our framework is useful for both microscopic classical stochastic systems where entropy production rate appears and quantum systems where transition energy appears. So yeah, here's a summary. Yeah, thank you for your attention.
Many thanks for Dr. Ryusuke Hamazaki's interesting talk. Are there any questions?
Thank you for your great talk. My question is, can you show some example of macroscopic transition that which the equality holds for your bounds?
Yeah, that's a very interesting and important question. And yeah, actually, there is a case where the equality was true. And well, for example, if we consider some one-dimensional system and particles may hop to the other sides. So this is a quantum system. And in this case, we find that some equality condition holds true. Equality holds true for speeds. But actually, we can explicitly write down when this equality condition holds true, but I don't know how to interpret physically now. So does that answer your question?
Yes. Thank you.
Yeah, thank you for your question.
Oh, yeah.
Thank you very much for great talk. And for the first part, maybe I missed it, but so about the critical scaling.
Mm-hmm.
So that sounds very general. And so my question is, did you use any specific structure of evolutionary dynamics to derive this, or does it hold for very general ODE, or if it is near transcriptical bifurcation?
Yeah, that's an important question, and I think that if the type of the bifurcation is the same, then it can be used for other type of the bifurcation, other type of the ODEs, general ODEs, but yeah, we did not show this. We have some evidence numerical evidence for this. For our systems, so we haven't proven it, but we conjecture that this is the case.
And thank you very much. And for the second part, so your new speed limit, actually, some people are also working on different types of speed limit where they are discussing it in relation to so-called Wasserstein geometry or optimal transport or something like that. So is there any relation to your speed limit? Or?
Yeah, I think it's quite related, and we do not optimize our bounds, but if we consider if optimizing this quantity, for example, under certain constraint, then it is very similar to the BB formula for Wasserstein distance. And so since this is a graph-based discussion, I don't think there is consensus for defining the Wasserstein distance under such graphs, but yeah, I think it's very related in that sense. Yeah.
Okay, thank you very much.
Any other questions? If no, then let's thank our speaker again. And
thank you.